All right, welcome back, class. Grab your seats. Today, we're jumping right into an explainer that literally decodes the chemistry of life. We're going to take this fascinating journey from the microscopic building blocks of carbon all the way up to the everyday items sitting around your house right now. I'm incredibly excited to guide you through this because, well, organic chemistry is essentially the blueprint of our entire physical world. So let's get into it. Here's our lesson plan for today. 1. Meet carbon's allotrope family. 2. Naming of the organic world. 3. The electron push and pull. 4. The ring of stability. And finally, 5. Polymers in everyday life. Section 1. Meet carbon's allotrope family. So carbon has this absolutely wild ability to link to itself, which is a property called catenation, and this allows it to create incredibly diverse physical structures that we call allotropes. It brilliantly illustrates how the exact same carbon atoms can produce two materials that literally couldn't be more different. For example, check out diamond. Here, carbon uses sp3 hybridization to bonds to 4 other carbons in this rigid 3D network with super tight 154 picometer bonds. It's like perfectly welded, indestructible scaffolding. But then, look at graphite. Here, carbon uses sp2 hybridization to form flat, planar hexagonal sheets stacked on top of each other with a 340 picometer gap between them. Those layers are held together by super weak van der Waals forces. That means they slide over each other effortlessly, kind of like a slick deck of cards. That's exactly why we use graphite as a dry lubricant in really hot machines, and, of course, as the lead in the pencil you might be holding right now. But carbon actually has another trick up its sleeve. If you want a fun analogy, just picture a microscopic soccer ball. I mean, literally a tiny soccer ball. That's the exact shape of a fullerene molecule, specifically Buckminster fullerene, or C60. It features exactly 60 vertices, with a single carbon atom at every single one, arranged perfectly into 26 membered rings and 12 5-membered rings. It uses this clever mix of single and double bonds to hold that perfect spherical shape. It is just a beautiful piece of nature's geometry. Moving right along, Section 2, Naming the Organic World. Now here is a visual cheat sheet straight from our sources. It shows the classic trivial prefixes we use to name carbon chains from 1 to 5 atoms long. In organic chemistry, the name actually tells you exactly how many carbons are in the chain. 1 carbon is form, like formaldehyde. 2 is acid, like the acetic acid you'd find in your kitchen vinegar. 3 is propion, 4 is butyr, and 5 is valor. Now, I know memorizing these prefixes can be a little tricky at first. So, to lock these into your brain, form, acid, propion, butyr, and valor, just remember this teacher-approved mnemonic: 5 awesome professors bake vanilla. Honestly, it works every time. 5 awesome professors bake vanilla. Keep that phrase in your back pocket and you'll always know the first 5 prefixes of the organic world. All right, Section 3, the electron push and pull. So let's look at how electrons actually behave inside these chains. The crucial concept here is the inductive effect. I want you to think of this as a microscopic game of tug-of-war. See, a normal carbon-carbon bond is nonpolar because both atoms are pulling equally. But the second you attach a different group, that balance completely shifts. Groups with a plus I effect are electron donating. They essentially push their electrons into the carbon chain. On the flip side, groups with a minus I effect are highly electronegative, meaning they greedily pull electrons away from the chain. And standing right in the middle, acting as the perfectly neutral referee, is the hydrogen atom. We assign hydrogen an inductive effect of exactly 0. Understanding this push and pull is literally the secret to predicting how a molecule is going to react. Which brings us to Section 4, the ring of stability. Now this is where things get really fascinating. Let's look at the classic benzene ring. You might see it drawn with alternating double and single bonds, but those lines you see inside the hexagon actually represent something called a resonance hybrid. What that means is the electrons aren't just locked in one spot. Instead, they are shared equally and continuously all the way around the ring. This constant sharing creates an unbelievable amount of extra stability, which is a phenomenon we call aromaticity. But nature has some very strict rules for what gets to be an aromatic compound. To get that special VIP stability and oftentimes a very characteristic smell, a molecule has to pass a strict checklist known as Huckel's rule. First, it must be cyclic. Second, it must be a flat, planar molecule where every atom is sp2 hybridized, allowing all their p orbitals to overlap perfectly. And finally, it has to contain a very specific mathematical count of pi electrons. It has to be exactly 4n plus 2, where n is an integer like 0, 1, or 2. If it passes that test, Boom. It achieves that legendary aromatic stability. And finally, Section 5, polymers in everyday life. For our grand finale, we're taking all these microscopic rules we just learned and scaling them up into the massive chains that you literally touch every single day. Look at how these kind of intimidating chemical names map directly to stuff around your house. Polymers are basically just giant molecular chains made by repeating a single basic unit, called a monomer, over and over again. When you link up thousands of ethylene monomers, you get polyethylene. That's the exact material making up your everyday plastic grocery bags and film wrap. Take vinyl chloride, link it all together, and you've got PVC. That's the rigid plastic in your water pipes and the flexible material in your raincoat. Or if you take tetrafluoroethylene and polymerize it, you get PTFE. You probably know it as Teflon, the perfect nonstick surface right there on your frying pan. And by the way, those were just addition polymers. Let's look really quickly at condensation polymers. It's just amazing to see how different chemical linkages can yield vastly different properties in the real world. On the left, we've got polycarbonate, also known as Lexan. Its specific bisphenol and carbonate linkages create a clear material that is literally tough enough to make bulletproof glass and heavy-duty bike helmets. On the right, we have nylon 6s6. It's a polyenamide formed from very specific 6-carbon chains. This creates a fiber that is so incredibly strong, yet lightweight and flexible, it can save a skydiver as a parachute or just be woven into the clothes you're wearing right now. We've traveled all the way from single carbon atoms to the complex polymers that totally define modern life. As we wrap up today's explainer, I want to leave you with this thought. If a single element can be both a soft pencil lead and a bulletproof shield, if it can form microscopic soccer balls and massive parachutes, what incredible material will organic chemistry discover next? Thanks for joining me for this lesson, class. Keep your eyes open because chemistry is absolutely everywhere.